Matthias, quick question. Is this supposed to work?
Close it.
So I'm going to present joint work with Dan Roy and Wasim Garbi. So just since this is a workshop, I thought I'll present some work that's ongoing right now. So this is work in progress. So just a warning before I start. So what might generalization theory offer deep learning? One thing we hope it might offer is explanation. So explanation of empirical generalization performance. We might expect it might offer ability to predict the results of interventions on the learning algorithm. The theory is very precise. It might even offer prescription for how to improve generalization, design new algorithms with improved generalization guarantees, or even do model selection. Now, I'd like to argue that what a lot of deep learning theory actually offers is merely suggestion. So it lacks explanation. The bounds that we have are empirically numerically vacuous and cannot explain generalization on their own as bounds, at least. So what people usually do is post hoc empirical correlation studies that provide some sort of evidence that the quantities in the bound are relevant. It also lacks prescription. So model selection using these bounds usually leads to severe underfitting. And this is because the bounds are loose, you're usually over-regularizing. Of course, people have turned quantities they find in the bounds into algorithms, but then post hoc empirical work is needed to actually tune complexity hyperparameters, again, not to over-regularize. So community has heavily focused on asymptotics of non-asymptotic bounds. And of course, this work is essential and foundational, but more attention needs to be paid to evaluating theory empirically and seeking complete understanding. So what could be a goal for statistical learning theory that could push things forwards? So one ambitious goal, of course, is finding non-vacuous bounds for stochastic gradient descent. Let us be the training sample and use some random source. Let each hat be the classifier produced by stochastic gradient descent with some hyperparameters theta that achieves 1% training error. Now the challenge is to identify a function psi and prove that with high probability, the risk for the classifier returned by stochastic gradient descent is upper bounded in terms of this function psi. So psi can depend on the hyperparameters, on the training set, on the random source, and psi yields a valid statistical bound. And a requirement is for psi to be better than a guessing rate, or ideally even tied close to the test error on standard benchmarks. Now, we don't have any non-vacuous bounds for stochastic gradient descent, but we do have bounds for stochastic neural networks or for compressed neural networks. So this is recent work by Zhou et al. Presented at ICLR this year. We also have bounds for differentially private stochastic gradient descent. So these are stochastic variants, like noisy variants of HGD. In all these cases, tighter bounds come at a cost of underfitting. So there seems to be a trade-off between how tight of a guarantee you can get and how good your classifier that you obtain is. So what are the barriers to explaining generalization? One type of barrier is statistical. So our bound might depend on quantities that we don't know, for example, on the unknown data distribution. And we only have access to the data distribution via samples. Now, best bounds are for undertrained noisy networks. So is it even possible to have tight bounds for high-performance networks? Another type of barrier is computational. So again, our bounds might depend on quantities that are intractable. And yet another type is analytical. And perhaps the right bounds, they may not even have been invented yet. So for the remainder of the talk, I'll revisit the PAC-Bayes framework for generalization bounds. I'll discuss 3 principles for obtaining tighter generalization guarantees, and I'll apply that for the neural network setting. So just a reminder, the last part of the talk will really focus on the ongoing work that's in progress. So PAC-Bayes bounds yield risk for Gibbs classifiers, which I will define in a minute. Let me introduce some notation first. So let H be the hypothesis class. Let L be the loss function that maps hypothesis and training data to a bounded interval 0, 1. Risk, as usual, will be defined as the expected loss, and empirical risk as the average loss over your training data. A Gibbs classifier is a probability distribution over your hypothesis class. So we can interpret this as a randomized classifier by looking at the definition of its risk. So the risk of a Gibbs classifier Q is the expectation over the draws from Q of the loss. So we can rewrite this expectation as a double expectation where we first draw a sample from the training data, from the data distribution, and then we draw a classifier and we evaluate the loss on this random draw. So let me now state the PAC-Bayes generalization guarantee for Gibbs classifiers. So for the remainder of the talk, we'll be dealing with bounded loss functions. Nature chooses a data distribution D. We choose a prior distribution P on the weights. So in this case, it's a Gaussian. The nature gives us a training data set S. Now we know the empirical risk surface. Then with high probability, for all posterior classifiers Q, the risk of the classifier Q is subbounded in terms of its empirical risk plus the scale divergence term between Q posterior and P prior classifier. So looking at this example on the right, we could place, let's say, a Gaussian posterior distribution Q in this minima region. We are allowed to have quite a bit of variance without incurring too much training error. And the scale divergence term between Q and P is probably relatively small, so we get quite a tight guarantee. Now we could also place a different classifier Q prime in this very kind of narrow minima region. Q prime has to be really concentrated, not to incur a lot of training error. So we want our training error to remain small, so it has to be really concentrated. And of course, now the scale divergence between Q and P is way larger, so PAC-Bayes gives a much weaker guarantee for this classifier Q prime compared to Q. We could rewrite this PAC-Bayes bound as a bound on the square generalization error. So we just rearrange some terms. And in fact, PAC-Bayes bounds can be proven for any convex function on the loss, on the risk and empirical risk. And then on the right-hand side, we get a scale divergence between Q and P and this log term that depends on the convex function you chose. So PAC-Bayes bounds are for randomized Gibbs classifiers. Yeah.
Can I just ask, so is part of the point that you don't know a priori how to choose Q in a principled way, and so you're kind of reduced to proving something that holds for all Q? It seems very strong to have a statement that holds for every Q.
Well, this gives you extra flexibility. So in fact, I'll be talking later that there are optimal Qs, but it really depends what algorithm you want to get guarantees for. So Q, like the most important thing here is that Q is data dependent, so it can be chosen in any way using the training data, and P has to be chosen before you get the training data. That's kind of the only thing that you care about. So yeah, PAC-Bayes bounds are for Gibbs classifiers, so randomized classifiers. And ideally, we want to get a guarantee at the end for a deterministic classifier that we get from HED. And there is a growing literature on techniques to construct PAC-Bayes bounds on deterministic classifiers. So one old idea is explored margin to de-randomize these randomized classifiers. So this particular picture is for SVMs from some older work. And more recently, people have kind of used these same ideas in the neural net setting. So for example, this result by Neishaber et al. So in this particular case, we first fix a margin gamma. Then for our deterministic classifier H, we construct a randomized classifier Q that satisfies this margin condition. So basically what we want is if we sample a classifier from Q, we want the output of the function not to change too much. So the perturbation has to keep you within the margin. Then with high probability, you get a bound on the deterministic classifier H. So the risk of deterministic classifier H is now upper bounded in terms of its empirical margin loss plus the scale term. So there are other ways to construct kind of de-randomized PAC-Bayes bounds. One of them is disintegrated versions of PAC-Bayes. This is work due to Cotoni. One of kind of more recent approaches is combining PAC-Bayes with generic chaining. Now just to recap, we want bounds for stochastic gradient descent, so for something for a deterministic classifier we get out at the end. So consider PAC-Bayes plus margin approach to bounding HED risk. In order to de-randomize, we need posterior Q that is tightly concentrated around the weights obtained by stochastic gradient descent. Now, in order to control the scale complexity term, we need the prior P to have sufficient mass near the stochastic gradient solution. And actually, these two things are really in tension, right? So there is like a trade-off kind of, for Q to be tight, you want the prior to be kind of wide and the other way around here. Now, this seems to be impossible without, let's say, knowing the data distribution or using some of the training data. How would we know where to center our prior P? So it seems to be hard. So people have attempted to just generally tighten PAC-Bayes bounds. Let me mention a few approaches. So one of them is optimize the posterior Q. So it's quite well known that for a fixed prior distribution P, there is an optimal posterior distribution Q, and it takes the following form. So its density is proportional to exponentiated empirical risk. Now, we will not be taking advantage really of this flexibility because we're interested in getting guarantees for a specific algorithm. And changing Q would be like changing your algorithm. Another approach towards tightening PAC-Bayes bounds is optimizing the prior. So for a fixed learning algorithm Q, so now Q is fixed, there exists an optimal prior. So again, this is older work. So the optimal prior is just the expected posterior distribution. Now to get this, we need to know the data distribution. And in our most recent work, we actually showed that you can optimize over the subset of the training data that you use to estimate the bounds. So I'll talk about this in a bit. So let me just tell you a little more about this approach for getting these optimal prior distributions. So optimal prior P is expectation of Q. So PAC-Bayes prior can depend on data distribution D, but it cannot depend on the training data S. But our only handle on the data distribution is via the samples we get. So how is this even possible? It seems, really hard, right? So people have tried, so there are a couple of different approaches that people have tried. One of them is distribution-dependent prior. So you construct some form of a distribution-dependent prior, which is theoretical prior, you don't really have access to it, but then you upper bound the KL divergence for this particular prior. A different approach is using data to construct the prior. So again, in 2007 to 2012, there's quite a bit of work on constructing data-dependent priors, really to get towards this data distribution-dependent prior. We also have work from last year. We use all of the training data to learn the prior, but in some safe ways. So in particular, we use differential privacy to formalize this. So Lever et al. In 2010, they studied priors and posteriors of the following form. The prior and posterior are, the densities are proportional to exponentiated true risk and empirical risk, respectively. So this prior is really a theoretical prior, right? We don't really have direct access to it. And both of these depend on this parameter gamma that we'll call inverse temperature. So the higher the inverse temperature parameter, so the lower the temperature, the more concentrated posterior distribution will be around its risk minimizer. What they show in this work that then the KL divergence between Q and P, so for these particular choices, can be upper bounded with high probability in terms of this inverse temperature parameter gamma. Now, of course, once we have the bound on the KL divergence, we can plug it back into any PAC-Bayes bound, really, and get a bound on the difference between risk and empirical risk in terms of this parameter gamma. So kind of data distribution dependence comes for this parameter, inverse temperature parameter. And if we need only small gamma to actually get pretty good empirical error for Q, then we'll have a tight guarantee. We validated these bounds empirically, so I think this particular plot is for MNIST data set. So these two overlapping lines are train and test errors. So a little higher one is the test error, the bottom one is the train error. The green line on the bottom is the generalization error, so just the gap between the two. So it's 0 for small values of gamma, and it's kind of still very small for larger values of gamma. One thing I would like to draw your attention to is that as we increase the parameter gamma, our generalization error doesn't really increase. In fact, it even looks like a little smaller here than, for example, here. Now this dotted line is lever bound on the generalization error. So initially it's quite tight, but as we increase the parameter gamma, it starts really exploding and becomes vacuous pretty much at the point when we're starting to learn. Well, not really, I guess. We're learning here, but it's kind of around here. What you care about is it's vacuous, and maybe here you can kind of get a guarantee. So it seems that this parameter gamma is really for kind of some kind of worst case scenario. And it comes from really upper bounding the Keele divergence. So on the right-hand side is the same plot for MNIST with randomized labels. So there is no signal in the data anymore. So the test error is always around the guessing rate. The training error decreases. So you need a higher gamma for the training error to be really small in this case. The generalization error is this green line. So initially it's 0. Once we start learning, it jumps to pretty much maximum. And the lever bound is this dotted line again here. So again, initially it's small, and as we increase gamma, it starts increasing. And you can see that actually it pretty well captures the true generalization error gap, which is the green line. So it does seem like this bound cannot really capture data dependence too well. So in summary, Lever et al. Bound is vacuous once gamma is large enough to fit random labeled data sets. Now recall that PAC-Bayes prior P can depend on the data distribution, but not the data itself. But the data is our only handle on the training data distribution. So the idea is to use some of the training data, to use all the training data, choose the prior P, but in a way that is stable to changes in the training data. So that the prior would be almost independent of the training data. So this is our work from our last year's paper in Europe's, where we show that if the prior P is learned in an epsilon differentially private way, then with high probability, we get exactly the same PAC-Bayes bound as before, but now with this additional error term that depends on the privacy level. So if prior P is learned with an algorithm that has a lot of differential privacy, so epsilon is really small, we'll have very small risk, small error, small additional penalty. If we have not too much differential privacy, epsilon is large, we'll incur a lot of additional error for using our training data.
Question about the plot on the previous slide. So this, if I understood correctly, this bound, you called it lever, right? Whatever you
I pronounce lever, but
okay.
lever.
Okay, so the lever bound. I'm a little confused because maybe I didn't understand the slide, but it was this Gibbs measure on the risk, gamma times the risk,
Yeah.
and so that thing is sensitive to labels. So I'm not understanding where this argument is.
Well, the upper bound and the Keele divergence, right? So you don't have access to the true data distribution. It's not that you can actually write down this prior.
I thought you were cheating somehow.
No. So in this case, like they take the prior and posterior this form, but then because they cannot access this prior in any way, they upper bound the Keele divergence. And really the looseness, I think, comes in this upper bound.
But what if we made a cheating bound where instead of using the Keele divergence, we Monte Carlo or whatever, and we actually evaluated this thing, and then it seems like it could be pretty good.
I'm not sure how Monte Carlo would help you cheat. You would still need, so maybe you could use on top some differential privacy or something, right? To be able to, or maybe a held out training set to estimate what the prior is. Maybe that's what you're talking about, having some.
The top line looks like it should be. It's sensitive. It can tell apart randomly.
I agree. So one thing we could do, I guess, we could take like a totally fresh data set from the same data distribution, evaluate, try to approximate this distribution-dependent prior, and try to see what the bound would look like then for these particular choices. So this is not the optimal prior, really, right? But it's still distribution-dependent. So maybe it's close. But of course, once you upper bound it, as they did, then you get this kind of like worst case, not real worst case maybe, but worst case type of thing. But yeah, that's one approach. You could see if that would really test how optimal this prior is in general. How close is it to optimal?
You answered my question. I was trying to figure out where the worst casing over labels in it, and it's between the two lines.
Yeah. So the challenge from using this differentially private PAC-Bayes bound is that differential privacy is hard to achieve. So one solution we propose is by showing that just merely being close in Wasserstein distance to a private mechanism suffices to yield a valid generalization bound. So you don't actually need a sample from a differential private algorithm, but it's enough to be close. Now there are some new other stability-related approaches by Rivas-Platt et al. From last year. So numerous approaches exist trying to approximate this optimal prior. It's either analytically, using data, or using privacy. But is approximating P star actually optimal? So this is the usual PAC-Bayes bound on the top. On the left-hand side, we evaluate the empirical risk term of Q on all of our trained data. And on the right-hand side, we divide by all of the number of samples we have in the training data, M. So this is just the size of your training set. Of course, you could reserve some data S prime and only evaluate the risk term on S not S prime. Then you're effectively divided by a smaller number on this right-hand side. And now you're allowed to use this reserved data to learn the prior. So if we only use S not S prime to estimate generalization error, then the optimal prior takes the following form. So it's a conditional expectation now of Q. Would we ever want to do this? So the answer is yes, and that's what we show in our most recent work. So even if you have access to the true data distribution, it's still optimal to use some of the data. So informally, there is a distribution loss in learning algorithms, in particular HUD in our example that we construct, such that a PAC-Bayes bound of oracle prior is vacuous, but same bound on a subset as not as prime of oracle prior, which is now this conditional prior, conditional expectation, is non-vacuous. So it's actually optimal to use some data even if you have access to the data distribution. Just to recap, in order to relate Q to kind of our original goal, so in order to relate Q to stochastic gradient descent weights W star, we need posterior that's tightly concentrated around the weights learned by stochastic gradient descent. And in order to control the Keil complexity term, we want to use now some data to approximate data-dependent oracle prior, which is the conditional expectation of Q given our reserved data. Then the empirical risk term in the bound is computed on S and not S prime, where S prime was used to learn the data. So how might we approximate this new data and oracle dependent prior? Yeah.
So should I think of this as being like, I get to choose S prime like at random? Doesn't matter, or do I have to very carefully curate which S prime?
Yeah, so you could choose it at random. If you carefully curate, you would need to add a penalty, maybe like by a linear boundary or something like that. If you like carefully choose what examples you want to use.
But somehow your theorem is okay if I just choose it, to be like half of the data at random or something.
Yeah. So it's totally like it's kind of obvious why you can move some of the data, but what's less obvious is that up till now, people only took those, like, the optimal prior is thought to be this only distribution-dependent prior, right? So the optimal P was expectation of Q. What really the theorem is about that not only you can move the training data and use some of the data to estimate the prior, but actually it's optimal in some cases. So that's really kind of the novelty. So consider a Gaussian prior P and posterior Q. So Q takes the following form. It's a Gaussian centered at the output of stochastic gradient descent with some diagonal covariance matrix. The prior is also a Gaussian, centered at some weights W bar that are learned from a subset of the data S prime and has isotropic covariance. So it's just lambda times identity. Then the Keil divergence between these two Gaussians takes the following form, and this part really depends on the weights and the prior variance, and this is just depending on the variances of prior and posterior. So once a prior mean W bar is fixed, we are free to optimize the diagonal covariance matrix of our posterior. Now we must choose the prior mean W bar before we see the full training data S. So ideally, we want W bar that minimizes this term that depends on W bar. So we end up with the following minimization problem. Now we cannot really solve this exactly, but like ideally we could, this really relates to kind of Wasserstein distance ideas and coupling, but I will not go into the details, and I will really just approximate it using stochastic gradient descent, and I'll tell you more in just a minute. So for stochastic gradient descent, I forgot to add, so of course we also have some other randomness used. So for example, what mini batch we choose. So we want to use stochastic gradient descent really to predict stochastic gradient descent. So W star should be equivalent to HGD on the full data set. And since S prime is a subset, is a random subset of all of the data, we're free to choose S prime to be first data processed by stochastic gradient descent. So we want S prime to choose, we choose S prime in a way that it's the same data that stochastic gradient and descent accesses for the first few iterations of training. So we'll approximate W bar by running stochastic gradient descent on this subset of S prime to convergence. And by design, stochastic gradient descent on S prime will match the initial behavior of stochastic gradient descent on S. We can just totally match it because we have access to the same data. So here is a toy example. These blue lines are just empirical risk surface. We run stochastic, we initialize stochastic gradient descent here. We run it. We end up at the minimum because it's a convex problem. Now we could place without knowing really let's say the data distribution or having access to the data, one thing that we could do for, as a default, as a baseline, we could center the prior distribution here. So here we center a Gaussian at random initialization. Now we could also, like I talked about in the previous slides, we could use some of the training data, so a small fraction of the training data to train the prior using stochastic gradient descent. So initially, both stochastic gradient descent, which is on full data, which is a blue line, and stochastic gradient descent on this subset of the data, they run together. And eventually, the green line just illustrates stochastic gradient descent running on the small subset of the data that the prior has access to. Now we can place a Gaussian here instead.
Oh, yeah. Why don't you finish the slide and I'll ask my question.
Okay. So we could place a Gaussian for the prior here, which is already a bit closer to the final weights achieved by stochastic gradient descent on all of the data. We could, of course, use even more of the data, or even more of the data. Now we're really close. But of course, the more of the data we use, the lower the number. So I don't have the PAC-Bayes bound here, but well, the lower the number is that we divide the KL divergence by. So there is a trade-off.
Yeah, sorry. So now we have, okay, we started with the bound where we compute everything a priori. Now we have a bound where we split the data into two pieces. We use the first part to estimate some parts of the bound, and then we use the second part for some other parts of the bound. So if I'm in this regime now where I'm splitting data using two halves for different parts of the bound, for me the natural baseline is just a validation. So I just take the other part of the data and compute, I just hit it with Hufting.
Yeah, so one thing is we don't take any data out of the original HGD run. So HGD is like the W star weights. So HGD on the full data, it's allowed to access all of the data. So we don't really split the data and give half of the data to the training algorithm that we care about and the other half just for validation. HGD is still learning on all of the data. But now we just use half of the data to learn the prior, and we're dividing by smaller numbers and evaluating the empirical risk number.
Okay, my question is still valid though. So let's do this then. So if we do your thing, we get some bound. And the other thing we can do is we train on the first half of the data, and I just use the other half of the data to create a validation error. So do you know how these two compare?
Yeah, so you'll be learning on half of the data, first of all, right? So you'll get potentially a worse classifier. Second, using this for validation, it doesn't give you any insight really why the algorithm works or it doesn't work. So the kind of what we're aiming towards is perhaps by doing this, we'll get to some structure that will then tell us why stochastic gradient descent generalizes or doesn't. Or maybe, some structure of interest that we could then use to get different generalization bounds. So just using held out data doesn't really tell us much. It might give a tighter guarantee at the end. Probably would, but it doesn't give us any insight.
Okay.
So this is a toy example. We apply it on neural networks too. So this particular plot is for fashion MNIST on a 2 hidden layer neural network, but we got the same results for MNIST, C410 on COMNETs and other fully connected networks. So on the x-axis, we plot alpha, which is a fraction of the data accessed by the prior. And on the y-axis, we plot the squared L2 norm between the weights learned by stochastic gradient descent on all the data versus weights learned by this fraction of the data. As expected, this distance is decreasing the higher the alpha. But of course, what we really care about is when this distance is normalized by the number of training data that we have left over that the prior hasn't seen. So even when we normalize, we see that actually it is better to use some of the training data. to learn the prior distribution. Now, here we also optimize the PAC-Bayes bound. So in the previous plot, I was just showing you the means, how the means get closer. Now here we also allowed ourselves to optimize the posterior variance, so how tightly we're concentrated around this HGD solution. And we evaluated the PAC-Bayes bound. So again, on the x-axis, you see alpha. So on the left-hand side, it's just a fully connected network. On the right-hand side, a convolutional network. On the x-axis, you see alpha. On the y-axis, the loss. The line with the circles is the test error or the randomized classifier, and this is the generalization bound that we get. So in both cases, we see that actually it is better, even numerically, to use some of the training data to learn the prior. Now, how well are we actually predicting the weights learned by stochastic gradient descent? So here on the x-axis are the weights learned from this prefix data, so from this fraction of the data that the prior can access. And on the x-axis, it's the weights learned by stochastic gradient descent running on all the data. So this is at initialization, comparing the weights at initialization versus the weights at the end of training. And the higher the value k, we see that we can actually, even for k equals 0.1, we can predict the weights pretty well. So it's somewhat surprising how well the weights are predicted. But it's still not good enough when there are millions of parameters. So the KL term is actually still large. So how do we make progress? We could perhaps make better predictions on the mean. So we could maybe decrease this squared L2 norm. But it's not clear this is possible. How much could a better prior covariance help? Because one thing we didn't really do is we didn't do anything clever with the prior covariance. So for Gaussian prior P, with diagonal covariance matrix, the KL term takes the following form. So how much could an oracle estimate of this lambda help? Optimizing the KL bound in terms of lambda, we obtain that the KL equals to this expression. So of course, we cannot do this to get a valid bound, but we just want to really test the limits. If some oracle came and told us what the optimal prior variance is, diagonal, how better could our bound be? So this bound represents the best we could hope to achieve and allows us to test limits of proposed mean prediction W bar. So this is the same plot as before. Now note actually that in these plots we learned only on half of MNIST data set for reasons that I might tell you about during the time. So on the left-hand side is again the fully connected network. On the right it's LINET 5. Now this is a bound as before where the prior variance is not really learned. Now if we set the prior variance to this oracle variance, we see improvement, and there is quite a bit of improvement, actually. And the bound does seem to be quite tight around here. In this case, we also tried to push this idea even a little more to the extreme. So we used something that we call the ghost sample. So as I mentioned earlier, this is only trained on half of the MNIST data set. So we used the other half to train the prior. Like, could training the prior on new, fresh data really help us? And actually, it barely helped, at least. But I'm not really sure this is due to some kind of is it due to optimization being hard, or is it actually kind of the limit of this? So on the right-hand side now, I just replaced the plot with learning on all of MNIST data sets. Actually, the bound does get quite a bit better compared to the left-hand side. And this oracle prior distribution, so we are given these optimal variances, gets pretty close to the test error. Now, of course, this test error, by the way, is for randomized classifier, and of course, it's still quite poor. But we are still getting quite a bit closer. So it seems that there is, like, if we could learn the prior variance in some way, we could improve the bounds quite a bit. So just to recap, using the fraction of the training data as prime, subset of S, to predict stochastic gradient descent on all of the data leads to significant improvement over prior centered at initialization. Now, those ghost samples did not really improve predictions, which is a little surprising, but as I said, maybe we can still push that idea forwards. Theory suggests this type of data-dependent prior may be necessary for tight PAC-Bayes bound. So again, as I explained earlier, the optimal prior in some cases is not just this data distribution-dependent prior, but it's actually optimal to use some of the training data to learn the prior, of course, and the data distribution, so you need both. And we're still far from studying stochastic gradient descent itself. So stochastic neural networks in our studies were severely underfit due to looseness of the KL term during PAC-Bayes optimization. We need to really understand the Pareto optimal frontier. So it would be nice to understand for a given risk called the randomized classifier how tight of a generalization bound we can get. Study of Gibbs classifiers concentrated near stochastic gradient descent weights may be fruitful or suggestive, really, in the language that I used before, testbed for generalization ideas. So kind of to address Matisse's point, we're hoping we can learn something from this and actually identify some structures that are relevant for generalization. A careful empirical evaluation, whether by bound evaluation or causal analysis, is necessary to judge our understanding. So we should not only just plot how correlated our bound is to the generalization error when it's orders of magnitude, when the bound is orders of magnitude larger potentially, but then we should also perform some causal analysis to really understand whether this quantity is of interest. Or of course, if we get the tight bound, then perhaps we don't need a causal analysis. Now, despite impressive progress by community, we're still far from understanding generalization in deep learning. Thank you.
So Karolina started late, so we have quite a bit of time for questions.
I have one question. So you mentioned that there is a way to relate the generalization for the stochastic classifier to a single classifier.
Yes.
But I mean, if you just consider the Gibbs distribution, there can be there can be equally good global minimums. They're very far away, so this Q is not really concentrated in one place.
Yeah, but we're free to choose the form of Q that we want, right? So for example, using those margin ideas, we would really want something concentrated to be able to exploit those ideas. I'm not saying that using margin is optimal in any way to de-randomize PAC-Bayes randomized classifiers and get actual bounds on the deterministic classifier, but it's just one idea. But in that case, we would want something tightly concentrated.
The Gibbs distribution won't.
The Gibbs distribution, if we could actually sample from Gibbs distributions, we could probably do a lot more and have different randomization strategies. But yeah.
Actually, just maybe a comment related to his question. So if you don't use a subset of the data to create the prior as you did at the end,
yeah.
we don't, if we just pick the prior naively, then we're forced to actually get a prior which puts maths on all the possible good points, which we know even just by permutation and silly things has to be a combinatorially large set.
Yes.
And so in fact, one thing that makes me wonder is that, so you used a subset of the data to construct your prior, but I wonder if just using the initialization alone as a prior, did you compare to that? Was that the k equals 0.0?
Yeah, k equals 0 point, and also
that was already pretty good, right?
It depends. So actually, in this plot it's terrible. So one thing to note is actually that this plot is not this can be done much better. This is due to optimization failure. I think you're talking about the means being pretty good. So in this case, for example. But yeah, just putting the prior to initialization. So Zico Coulter, for example, or in his student, right, they had those experiments where they show that the distance, this L2 distance to initialization, doesn't kind of decrease as fast as you would like for the bounds, as you're increasing M, right, the number of training data. So other people have done experiments like that, kind of, seeing how important initialization is. And in our old work, we used B-centered tyrant prior set initialization. But in that work, we also allowed the posterior mean to deviate from a GD solution. So there we also optimize where we'll center Q. In this work, we really try to fix Q that GD found and then construct bounds. In this case, having the prior to initialization is actually not that good. I think what's really surprising is that now even using this ghost sample, so for k equals 0, this is just using all fresh data to center the prior. So we run GD on a fresh data set and we center our prior there. That it didn't really help much. So it seems that stochastic gradient descent, as trained on vision image data sets and training on neural networks, it's quite predictable when you use a subset of the data, but it's not really predictable when you run stochastic gradient descent on fresh data.
So generally, in generalization, deep learning, so there are different types of complexity measures, and they all provide upper bounds, right? And so for PAC-Bayes, I guess in high level, based on the distance between the final distribution and what we started off from.
Yeah.
So I'm not aware of any methodology we have right now for understanding if this is really what's driving generalization besides experiments. So can you comment on the type of experiments you're aware of that kind of try and evaluate this hypothesis that this is what is really controlling the generalization?
That the KL divergence is really what's controlling generalization?
In very high level, even not specifically KL,
Yeah.
but like for example, maybe somehow average over many runs and see if there's a correlation between the final generalization and how far the distribution is, or in some sense.
Yeah, so I would say, so we do actually have some experiments, but again, it's ongoing work for trying to predict the distribution of stochastic gradient descent in some sense. So as you said, averaging over multiple runs. And so that work is really ongoing, and I cannot, I guess, tell you kind of exact conclusions. But I think this is really trying to understand whether KL divergence is interesting, or maybe what kind of, we have a lot of flexibility in PAC-Bayes bands, right? What kind of distributions we choose for Q and P, because we can choose really anything.
Yeah, we think
So,
of P usually as the initial.
Yeah, so we could, if we are running instead of SGD, we are running SGLD, and SGLD converges weakly to a sample from a Gibbs distribution, then perhaps we can evaluate something, how relevant these PAC-Bayes bounds and the KL complexity term is. But for SGD itself, it's a little, like there is no stationary distribution potentially, right? It's a little harder to actually say with certainty whether this is a quantity of interest or not, just because of like all the choices for Q and P we could make.
But it could be could be the situation for other complexity measures that this is not really what's going on and there's something else, right? That's
Oh
one
yeah,
of
of
the
course.
difficulties in
Oh yeah,
generalization.
of course. I'm not saying that this is the approach we have to take, but this is like we're really just trying to understand how informative it is.
So yeah, relatedly, part of the reason I asked about the cross-validation thing is by baking in, so we know that gradient descent, the norms of the parameters go like log t. We know that a lot of the very late dynamics are determined by the intermediate dynamics. So you know that if you create your prior halfway through, you've kind of already baked in a lot of what's going on.
Yeah.
And so I'm worried that the explanatory properties of your bound are actually, maybe the bound is lower, but the explanatory properties are actually diminished by baking so much into.
Yeah, so it's interesting, though, of course, I would need to think more about it, I think. I'm still not really, I don't think that we're definitely excluding any explanatory power by this, right? So it really depends whether you want to explain the bulk of generalization error or the last few percentage points. So I think it kind of relates to that. There's still enough structure, though, left, right? I mean, you can still, if, for example, they didn't work, I think there is still quite a bit to tell. If they do work, we can say something about predictability of stochastic gradient descent, how predictable it is from the subset of the data. So I think that's already informative.
Also, you're stopping it halfway through the first epoch. You run these things for many epochs.
Yeah, you're saying, yeah, and in particular, the training and test are still very high when you choose your prior.
Yeah.
So it's actually not, there's a lot of work left to do.
I have a more philosophical question, which not just for PAC-Bayes bounds, but generally, if we are going to prove generalization bounds and test it on these few data sets, isn't theory overfitting to those data sets? Could it be?
We haven't managed to fit even one, I think.
So when you use S prime, the subset of S, to estimate the output of SGD, do you use the same random initialization, or you?
Oh yeah, I start from the same random initialization for sure. Otherwise, I think the results would be quite different.
Actually, maybe we should take our